In this video lesson, we're going to take a look at something called specific heat. That is the main objective behind this lesson. In order to understand specific heat, we first have to take a look at a few things. Remember in the last video lesson that we learned that heat and temperature are not the same thing. However, they do relate to one another. For instance, suppose you take an object and you increase its temperature and it raises. If the temperature raises, what can we assume about the heat involved? We would assume that if temperature is going up, the heat must be going up as well. And if temperature was going down, heat must be removed. So in essence, we can come up with something that looks like this. Heat, represented by Q, is equal to a change in temperature. The higher the temperature, the more heat. But there's something else going on here as well. Let's take a look at a more specific example. All right. Remember, we ended here last time. Q equals delta T, meaning heat equals change in temperature. But take a look at the two cases of water. The first one's a bottle of water. The second one is a gallon of water. Suppose I put in the exact same amount of heat into both containers of water. Would you expect their temperatures to rise equally? No. You would say that the temperature of the water bottle would raise higher than the temperature of the gallon of water. Now, why is that? You're putting the same amount of heat in. The reason is because the amount is different. You have more water in the gallon than you do in the bottle. Because the bottle has less water than the gallon, its temperature would rise higher. So there must be another factor at playing than just heat and temperature. Amount must play a key factor as well. We choose to represent amount in mass. So now we get to this point right here. We know that Q equals mass times delta T. But now let's take a look at another situation. Suppose we have our gallon of water, but then we also have a gallon of gasoline. If I were to put the same amount of heat into both containers, would you expect their temperatures to rise equally? After all, their mass is equal as well. The answer is no, you wouldn't expect that. You would expect the temperature to raise differently for each case. But why is that? The answer is because they're different substances or different compounds. So in addition to there being mass and delta T affecting how much heat, there must also be a third factor. And that third factor is known as specific heat. When you're looking at specific heat, it tells you how much heat is gained or lost during a particular reaction. Here is the final equation that we get with specific heat. We get Q equals M times C times delta T. Now let's make sure we understand the units that are involved in this reaction. Q, remember, equals heat, and heat is measured in joules. M stands for mass, and mass is always measured in grams. Now I'm going to skip C for a second and go right to delta T. Since it's temperature, our temperature is always measured in degrees Celsius. So what must be the units for C, or specific heat? In order for the grams and degrees Celsius to cancel out, the units for specific heat are as follows. Joules per gram degrees Celsius. Now, this is kind of a weird unit, but let's explain why the units are joules per gram degrees Celsius. The first reason is a mathematical reason. Remember, we want to get heat left over on the left side, which is joules. So that means the grams and the degrees Celsius must cancel out. But notice, the grams here and here cancel out, and the Celsius here and here cancel out, leaving joules behind to be our answer. The second reason is the actual definition behind specific heat. On the right-hand side of the page, you'll notice that it has a chart with a lot of different compounds and their respective specific heats. First, I'm going to explain what specific heat is, and then I'm going to explain what those values actually mean. The definition of specific heat is the amount of energy that is required to raise 1 gram of a substance by 1 degree Celsius. That's how we get the units of joule per gram degrees Celsius. It's telling us how much energy is required to raise 1 gram of a substance by 1 degree Celsius. Let's take, for instance, water in the liquid phase. Water has a specific heat of 4.184 joules per gram degree Celsius. Now, what does that actually mean? Well, suppose I had a beaker that had exactly 1 gram of water in it. Now, suppose that 1 gram of water was at 19 degrees Celsius, and I wanted to raise the temperature of that 1 gram of water by 1 degree Celsius, or in other words, to 20 degrees Celsius. How much energy would I have to put in that 1 gram of water to raise it by 1 degree Celsius? The answer is 4.184 joules. If I put in exactly 4.184 joules of heat energy into that 1 gram, the water would raise exactly 1 degree Celsius. That is how we can interpret all the specific heats that are given in this chart. Now notice the elements or substances at the bottom. They have very low specific heats. Anything that has a low specific heat will heat up much quicker. Notice that they're all metals, and that's why metals seem to get hot very quickly. However, the substances that are near the top have high specific heats. High specific heats just means that it takes more energy to raise 1 gram of a substance by 1 degree Celsius. In other words, it takes longer for it to heat up. A common example of specific heat is cool decking around a pool. Suppose you have a pool, and around that pool you have two different types of platform. On the one side, you have a platform that is cool decking. On another side, you have a platform that is cement or concrete. Which one would you expect to feel hotter? The answer you'd say is cement. But why would cement feel hotter than cool decking? After all, if you have the sun shining down, they're both experiencing the exact same amount of heat energy, and they both are roughly the same mass or same amount. So why, if the temperature and heat from the sun is the same and the amount is the same, would cement feel hotter? The reason why is cement has a much lower specific heat than cool decking. If you look at the chart, cement or concrete has a specific heat of roughly 0.84 joules per gram degree Celsius. What that means is it only takes 0.84 joules to raise 1 gram of cement by 1 degree Celsius. And I'll tell you what, the sun gives a lot more energy than 0.84 joules, which is why it heats up extremely quickly. Now, cool decking is not on this list, but we're expecting cool decking to be a very, very high number, probably higher than water. Since it has a high specific heat, it takes much more energy to heat the cool decking up, and therefore it'll feel cooler. Now that we have an idea of what specific heat is, let's actually take a look at a few examples. All right, let's take a look at this case. How much heat is released by a 44.7 gram piece of lead when its temperature decreases by 65.4 degrees Celsius? The specific heat of lead is 0.129. When you get to these problems, it's extremely important to make sure you analyze the problem. In other words, write down what you know and use that to help you what you're trying to find. All right, I'm going to go through and do that right now. I have 44.7 grams piece of lead. So right away, I know my mass is 44.7 grams. I'm also told that the temperature decreases by 65.4 degrees Celsius. So my change in temperature, or delta T, is 65.4 degrees Celsius. Now I'm going to make that negative. And the reason why I'm going to make it negative is because I'm told that the temperature is decreasing. If temperature is decreasing, it must be going down, and therefore the change must be negative. At the very end, I'm told the specific heat of lead is 0.129. Remember, the symbol for specific heat is C. All right, I have M, I have delta T, I have C. The last thing that I must be looking for then is Q. And since it's saying how much heat is released, I know heat is always represented by Q. So I'm going to look at my specific heat formula. Q equals M times C times delta T. And I'm going to plug in the numbers that I have. I know my mass is 44.7 grams. I know my specific heat for lead is 0.129, and I know my delta T is negative 65.4 degrees Celsius. By multiplying those three numbers together, I get the amount of heat that is released by the lead. And the answer with correct sig figs is approximately negative 377 joules. Notice that the sign of heat is negative. By having a negative sign, that tells me what kind of reaction is happening. It is released. And if you remember, when energy is released, that is an exothermic reaction. So we see by calculating Q, we not only can tell how much energy, but we can also tell what kind of reaction it is. If Q is a negative sign, that means the kind of reaction must be exothermic. If Q, however, is a positive sign, that means the reaction is endothermic. Let's give you one to try now. Go ahead and pause the video and work this one out. Then play the video and we'll work it out. All right, the question is asking how much heat is absorbed. Remember, it's asking for heat, and heat is always represented by Q. I'm told my mass is 98.4 grams, and I'm told the temperature increases by 13.4. Since it increases, I'm going to keep it positive. Finally, the specific heat of water is 4.184. Now knowing everything that I need to know, I'm going to plug it into my formula. Q equals M times C times delta T. When I calculate that, 98.4 times 4.184 times 13.4, I get my approximate Q. My Q value to the appropriate sig figs is 5,520 joules. Since it's positive, I know that this is an endothermic reaction. The last thing what we're going to do is we're going to take this idea of specific heat and combine it with our knowledge of law of conservation of energy. This is exactly what you guys are doing in your lab, and so this will be helpful. Let's look at the situation that we're looking at. We have a piece of metal that has a mass of 27 grams, a temperature of 175 grams, and a specific heat that we don't know. We do not know what this metal is. Now, what we're going to do is we're going to figure out what the metal actually is for this problem. Now, this metal is going to be dropped in a beaker of water that is 31 grams and has a temperature of 26 grams. Now, since we know that it is water, we do know the specific heat. It is 4.184. Now, when you put these two objects together, the temperature is going to even out for both and give us a final temperature of 49 degrees Celsius for both metal and for water, because they reach equilibrium when they're put together. Our ultimate goal is to figure out what is the specific heat of the metal. All right, that's easy enough. We can go ahead and look at this. I know my M, I know my T. I want to solve for my C, so I need to know my Q for the metal. The problem is I don't know how much heat is released by the metal. I can't solve for this alone because I have two variables, the C and the Q. Therefore, I need to do something else before I can look at the metal. If I look down at the water, though, I can solve for Q. I know my mass, I know my temperature, and I know my specific heat. So I could solve for the Q for water. Well, let's go ahead and do that right now. My Q for the water is going to be equal to the mass, which is 31, times the specific heat, which is 4.184, times the change in temperature. The water was originally 26, but it increased to 49. That change in temperature is 23 degrees Celsius. Notice it's positive because it's raising instead of lowering. By multiplying those three numbers together, I'm going to get the amount of energy absorbed by the water. My water absorbed approximately 2,983 joules. Now, according to the law of conservation of energy, if something gains a certain amount of energy, it must have lost it from something else. Well, now let's think about this. if the metal were to drop in the water, causing the water to gain a positive 2,983 joules, where did that energy come from? It came from the metal. So if the water gained 2,983 joules, the metal must have lost it. And so by doing that, we have just figured out what the Q is for our metal. It's negative 2,983 joules because the metal gave up that amount of heat to the water. Now look what we have done. We know the mass, we know the temperature, and now we know the Q for our metal. Now we can solve for our C. So we set it up like this. In our Q equals M times C times delta T, but now we're looking at the metal. I know my Q is negative 2,983. That's equal to the mass of the metal, which is 27, times my C, which I'm solving for, times my delta T. Now for the metal, it was originally 175, and it went down to 49. So I know it's going to be negative. And specifically, it's going to be negative 126. Now all I have to do is solve for C. By doing so, I get approximately, for C, 0.877 joules per gram degrees Celsius. I have just figured out what the specific heat was of this metal. Now this problem was a little difficult, and so I'd recommend is go back and watch my steps again. But before you do that, notice the steps that I had to go through. The first step I had to go through was figure out what was the Q absorbed from my water. We found that out to be 2,983. The second step was to figure out that if the water gained that amount of energy, the metal must have lost that amount of energy, making it negative. The third step, finally, was using all that information to determine what the specific heat was for the metal. This concludes the video on specific heat.